I was recently invited to a Vector Institute workshop, which was held at the University of Waterloo, and here I am giving my talk about improving the Gaussian approximation in neural networks. This is going to be a workshop paper at the NeurIPS conference coming up in Vancouver. It's sort of a very technical approximation of the output of a neural network using something called an Edgeworth expansion. So this can be a very technical math topic with lots of complicated things, but to try to make it a little bit more fun, I used the Alice heads versus Bob's heads tails problem as a motivating example in my talk. And so what I thought I'd do is make a YouTube version of this talk where I'm going to show you the Alice heads versus Bob heads tails in a little bit more detail, explain what an Edgeworth expansion is and how you can use it to solve this Alice versus Bob problem, and then relate it to my work on neural networks right at the end. So here's the infamous Alice heads versus Bob heads tails problem. We flip a fair coin 100 times to get a sequence of heads and tails. Every time we see heads in that sequence, Alice gets a point, and every time we see heads tails in that sequence, Bob gets a point. And the thing that's a little weird is when a lot of heads overlap, Alice can score a lot of points. So for example, in the sequence tails, heads, tails, there's 3 heads in a row, and Alice scores 2 points there because there's the first heads, and then there's a second heads, and they overlap. So Alice gets 2 points here, Bob only gets 1 point for that final heads, tails. And the question is, who is more likely to win at the end of 100 flips? Who is more likely to have more points? A lot of people on Twitter thought it was equally likely. That is wrong. One of them has a slightly higher chance to win than the other, just about 2% higher than the other. If you've never seen this problem before, I made a video a while ago with a really intuitive explanation of why one of these players is more likely to win. That involves a really fun analogy with a dog. But in this video, I'm going to tell you a completely different reason to think about why Bob is the winner. So Bob is the winner, or he's more likely to be the winner, and it has something to do with these overlaps. So some people in the previous video had some excellent comments, and they said things like, oh, Alice has a higher maximum score, and that means that she's less likely to win. Why is this the case? So it really does have something to do with the overlaps, and this method of using something called an Edgeworth expansion can really turn this overlap thing into a precise mathematical calculation that tells you who is more likely to win and by how much. So not only are we going to figure out that Bob is more likely to win, I'm going to try to explain this plot, which I showed in my previous video. This plot shows you for any length of game. So the original problem was with a length 100 game, 100 coin flips. But for any length of game, you can see that Alice is always not winning as often as Bob. So Bob always has the advantage. Those are the B's up there in the corner. And Bob's probability of winning is getting closer and closer to 50%. Alice's probability of winning is getting closer and closer to 50%. And these little triangles, these deltas, are Bob's advantage. Bob's advantage is getting closer and closer to 0 as the length of the game is longer. So a very long game, Bob has a very small advantage. In a very short game, actually for a game of only length 3, for 3 coin flips, that's Bob's highest advantage, and it's all the way up to 1/8. So Bob's advantage is shrinking as the length of the game gets longer and longer. And not only that, it has a really interesting formula. So the chance of a tie in this game is 1 over square root of pi t, where t is the length of the game. And Bob's advantage is exactly half that, 1 over 2 square root of pi t. And this approximation is extremely accurate. So for the length 100 game, it tells you that Bob's advantage is 2.82%, 1 over 2 square root of 100 pi. And this is accurate to 0.002%. So extremely accurate. And in this video, I'm going to use this Edgeworth expansion and talk about overlaps to try to show you why this formula is true. So here were some of the most popular comments from my last Alice versus Bob video, and people were noticing exactly the idea that I'm about to present here. So 3 Snow says, interestingly, the expected value of the score difference is 0. This is exactly right. Alice and Bob on average have the exact same score. So how is it that Bob is winning more? Well, it doesn't contradict this result. Alice's less frequent victories simply have a larger score difference on average than Bob's more consistent victories. So on average, they score the same. It's just that when Alice wins, she's winning by a lot of points. And when Bob wins, he's winning by just a couple points. And so Bob is able to win in more universes. Like the chance of Bob winning by a tiny bit is larger than the chance of Alice winning by a lot. So they have the same average score, even though Bob wins more often. Another user also did this. They said, this is actually how I came to the same answer. Their average result is the same, so the average score difference must be 0. Alice can win by larger margins, so the distribution must be skewed. This is exactly what I'm going to present in here. I'm going to explain this skewed distribution idea and use it to get that formula with the 1 over 2 square root of pi t. And I'm going to start with the example suggested over here. Just look at 3 flips. It's easier to see when you look at 3 flips. Bob wins by 1 in 3 of the games. Alice only wins twice, but wins by 2 in one of those games. So it's exactly this idea of Alice winning by more in fewer games. Let's see exactly how that works. All right, so let's answer the question, what happens when there's only 3 coin flips? This was suggested to us by one of the commenters, and we're going to see that this illustrates the idea that we're going for, that Alice wins by more because of a skewed distribution. Let's see what's going on here. So when there's 3 coin flips, there's 8 possible ways the coins could come out. Heads, 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 all the way down to tails, tails, tails. In each of these cases, you can figure out what is Alice's score and what is Bob's score. And then you can ask yourself, how are Alice and Bob sort of distributing their points amongst these 8 cases? So this is, I think, the key insight. You can kind of think of this as there's 8 possible universes, and Alice and Bob are each sort of choosing to score or not score in each of them based on whether or not heads comes up or heads tails comes up or whatever it is. And it's how they distribute them amongst these 8 universes that matters. So let's do Bob first. And I'm really using the fact that Bob, on average, will score half a point in 3 flips. And that's because he scores a quarter of the time he scores in the first 2 flips, a quarter of the time he scores in the second and third flip, the last 2 flips. And so altogether, he's scoring half a point. A quarter from the first 2, a quarter from the last 2. Altogether, on average, he scores half a point. And because there's 8 universes and he scores half a point on average per universe, that means he sort of has a total budget of 4. He's got 4 points that he's got to distribute amongst these 8 possible universes, and that is how he will choose whether or not to score or not. So once again, this is all kind of a thought experiment because, it's really dictated by how the coins come up, but this is a kind of equally good way to think about it. Actually, there's a game called the Colonel Blotto game that is very similar to this. If you play the Colonel Blotto game with 8 battlefields, that's exactly what Bob is doing over here. And Bob, very sensibly, he distributes his 4 points of budget amongst 4 different outcomes. So there's four different places here where heads, tails comes up, and Bob sort of puts 1 point into each of those 4 things. He's out of points. In the other 4 categories, he's going to have 0. I did a little dot for 0, so there weren't too many zeros all over. So Bob very sensibly puts 1 point on each of these 4 things that have a heads, tails, and he puts 0 points on the ones that have no heads, tails. Let's see what Alice does. So Alice, like Bob, has a average score of a half. She scores a quarter of the time in the first 2 and a quarter of the time in the last 2. So altogether, her average score is a half. And that means she has the same budget as Bob. And this is why the problem is kind of tricky. Her budget is also 4. So you might think that they are going to, win an equal number of times. But let's see what happens when Alice distributes her budget. So Alice has a budget of 4. The first thing she does, she puts down 1 point into 2 different places. So heads, heads, tails, and tails, heads, heads both get 1. And now Alice has a budget of 2 left over, which she could distribute amongst these 8 battlefields. And there's a lot of ways here that Alice could put her budget of 2 to equal Bob. So for example, she could put her budget of 2 and take these 2 that Bob is winning, heads, tails, heads, and heads, tails, tails, and put 1 point in each of them, and then perfectly tie Bob. Or she could take some of the ones where Bob didn't score and, claim a win on those. But Alice does something extremely silly here, which she takes 2 points and puts them into 1 universe, into the heads, heads, heads universe. So Alice uses 2 out of her 4 budget on that 1 outcome, heads, 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 and she's winning by 2 in this situation. So she's kind of like overkilled it on heads, heads, heads at a cost of having no budget left over to put in the other battlefields. So she's not scoring at all in these other battlefields. She's putting 2 points into heads, 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 and this is ultimately why Alice is not doing well. So let's take a look at the final tallies here. How often does Alice win? How often does Bob win? And how often is it a tie? Well, there's 3 places where Bob won. Those are all 3 places where Alice scored 0 and Bob scored 1. There's 3 places where there's a tie. 2 of them, they both scored 0, and in one of them, it was 1-1. And last but not least, Alice only wins in 2 different outcomes, in heads, 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 and in tails, heads, heads. And because Alice decided to put 2 points into heads, 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 that's really why she was not able to win a third of these outcomes, right? She was only able to win 2 outcomes because she kind of wasted her points by putting 2 points into heads, heads, heads. This is what those commenters were talking about of saying Alice is winning by more, but less often. And another equally good way you could look at this is to see that the string heads, heads overlaps itself. And that is what caused Alice to waste her points onto heads, heads, heads. So it really is this like self-overlap property of the strings that is leading to this feature that Alice is scoring by too much. So let's go into detail on this overlap thing, and it's going to tell us exactly how to calculate the skewness of the distribution. So now let's try to make what we were doing in the case of 3 coin flips precise, and let's try to extend it for any n and see if we can figure out how we can relate this overlapping of itself to the probability that Alice wins or Bob wins. And to do this, I'm going to define something called the hanging overlap of a string. So the hanging overlap of the sequence heads, heads, it's going to be a non-random number that tells you sort of how badly does heads, heads overlap with itself. I'm going to do the same thing for heads, tails, the hanging overlap of heads, tails, and we're going to see that by comparing just these numbers, the hanging overlap, you can figure out who wins through some nice mathematical theory. So what is the hanging overlap of heads, heads? Here's how you calculate it. You write heads, heads above itself twice. So heads, heads on top, heads, heads on the bottom. Then you shift it over just a little bit, and then you compare, and you notice there's a heads overlapping between them. And when there is an overlap between the two sequences, you count how much is overhanging. So in this situation, there's just one character, that final heads, that is hanging off the edge, and that will give a contribution to the hanging overlap. The hanging overlap is going to be a sum over all the different ways you can slide the string over and achieve a match. In this case, there's only one way you can slide it over and achieve the match. You slide it over by 1, and the match is exactly here. You have an overlap of 1 and a hanging off by 1 character, and the rule is you do 1 over 2 to the power of the number of characters that are overhanging. So in this case, it's exactly 1/2. The hanging overlap of heads, heads is 1/2 for that little extra heads that's hanging off the edge. And this actually comes from a probability calculation. It comes from the probability calculation of asking, if you've seen heads, heads already, what's the probability you're going to see another heads, heads that is overlapping with the first one? And in this case, you have heads, heads already. The chance of getting another heads for that last little coin flip is going to be 1/2. That's exactly what the hanging overlap is. Let's look in contrast to this at Bob's sequence heads, tails, which is going to be very different. So let's calculate the hanging overlap of heads, tails. And the hanging overlap of heads, tails, you start with heads, tails, you shift it over, and you notice there is no match at all here. Because there is no match, the hanging overlap for Bob is 0. It's impossible for Bob to score overlapped with himself. So given that a heads, tails came up, what's the chance he will score again overlapped with himself? The chance is 0. It's impossible for Bob to score overlapped with himself. So these quantities are the hanging overlap. I have a nice little document. You can see the precise mathematical definition if you want, but let me tell you the results of how these hanging overlaps matter for coin flip games. So viewers of my channel might have seen my video on the abracadabra theorem that I made a few years ago, and this already contains in it these hanging overlaps. So the abracadabra theorem answers a question, how many coin flips on average does it take until you see a given sequence? So for the sequence heads, heads, how many coin flips on average does it take until you see the first heads, heads? This is the same as asking in our game, how many coin flips until Alice scores her first point? And the abracadabra theorem tells you it's related exactly to the hanging overlap. It's always 2 squared, because they're sequences of length 2, times 1 plus the hanging overlap. For Alice, that is 6 coin flips. It takes 6 coin flips until you see your first heads, heads on average. For Bob, because the hanging overlap is 0, that's only 4 coin flips. And this is a very surprising thing, that it takes fewer coin flips for heads, tails to come up for the first time than it does for heads, heads to come up for the first time. And again, it's all because of these overlaps. There's a very clever martingale proof that uses gamblers at a casino to prove it. If you haven't seen that video before, I'll link it over here. In our case, we care not about the first time that things come up. We care about this thing, Alice's score minus Bob's score in n flips. That's a random variable called xn, and we can calculate this quantity, which is related to the skewness of xn. It's the expected value of xn cubed divided by the expected value of xn squared. So it's like the ratio of the third moment to the variance. Now that's because xn is a mean 0-centered random variable. And this thing, it turns out after a lot of work, you can prove that it has a very nice formula, which is it is simply the difference. It's the hanging overlap of Alice minus the hanging overlap of Bob, and this will work no matter what strings they have. So in our case, they're heads, heads, and heads, tails, but you could do the same game with different strings and you would get the same kind of result. The only thing that matters for this skewness is the difference in this number, the hanging overlap. And the skewness tells you sort of like how the distribution is tilted. So if it's tilted one way, we say it has a positive skew. If it's tilted sort of the other way, it sort of has a negative skew. And whose hanging overlap is bigger is telling you, is this skew positive or negative? And now you can turn this calculation for what is the value of the skewness, you can turn that into an exact calculation for what is the probability that xn is either bigger than 0 or less than 0. This is the calculation that uses a technique called an Edgeworth series expansion, and this is what is connected to my research on deep neural networks. But to summarize it for us, if the Edgeworth series expansion holds, then the probability that Alice wins minus the probability that Bob wins, it's related exactly to the skewness of the distribution, and you get this as your final answer. It just depends on the hanging overlap of heads minus the hanging overlap of heads-tails. And you can see it's with that negative sign. So whoever's hanging overlap is larger will lose the game more often. So in other words, this little calculation over here shows you that because Alice's sequence overlaps itself more, therefore Bob is the winner. He's going to win this game more often than Alice, and it also explains by how much. I left one little mystery quantity over here, the sigma n. That is the variance of the game. You can also calculate the variance of the game in terms of overlaps of Alice's sequence and Bob's sequence, but it's a little bit more complicated. It involves, you have to overlap heads with heads-tails and heads-tails with heads-heads. So you have to do a whole bunch of overlaps to calculate that variance sigma n. But if you just want to know who wins, then it's just literally the difference of these two numbers, a half and 0. And because Alice overlaps more than Bob, therefore Bob is going to be the winner. In the next part of the video, I'm going to show you sort of where this kind of calculation comes from. It comes from this Edgeworth series expansion, and that is what connects us into the deep neural networks world. So in this part of the video, I'm going to try to explain what is an Edgeworth series expansion for a random variable. And you should think of this as trying to approximate a random variable extremely precisely. So you want to be able to approximate a random variable, but you need to do it really, really accurately. And here is my example. So I have xn, which is Alice's score minus Bob's score. That's what we've been working on. The first kind of most simple way you can approximate the distribution of xn is to use the central limit theorem. The central limit theorem is everybody's favorite approximation theorem for random variables. There's an excellent series by 3 Blue 1 Brown on this distribution. I have a nice video with my favorite proof of it. And it's this distribution, this beautiful bell curve over here, 1 over square root of 2 pi e to the minus x squared. Very nice distribution, very nice approximation. It only has one problem for us though, which is if you want to know the difference between Alice winning and Bob winning, and you use this approximation, because it's completely symmetric around 0, right? The chance of it being bigger than 0 and the chance of it being less than 0 are identical. We're getting that the difference is approximately 0. So the central limit theorem Gaussian approximation says, okay, the chance of Alice winning is about the same as the chance of Bob winning. And that doesn't help us, right? We want to know who is more likely to win. The central limit theorem is not accurate enough. So what we need to do is we need to use a more accurate approximation for this random variable xn. So here's the next order. We don't use this purely Gaussian distribution. We use the Edgeworth series with one term. Here's what it looks like. So in this beautiful slime green color over here, I have plotted the Edgeworth series approximation with one term. And just like the central limit theorem that approximates distributions by the Gaussian distribution, the Edgeworth series expansion says that you can approximate a distribution by this funny looking density function. And the density function, it starts out exactly the same as the Gaussian bell curve. It's e to the minus x squared, same kind of curve we had before, but there is this correction term. And the correction term depends on this thing h3, which is the third Hermite polynomial. So it's this thing that comes from a famous mathematician, Hermite, and he found these polynomials. They are orthogonal polynomials. They're perpendicular to each other in some sense. And they're very special polynomials for the Gaussian bell curve. And it turns out you can make this approximation and it is more accurate than the pure Gaussian approximation from the central limit theorem. And the correction depends exactly on kappa 3. That is the skewness of the distribution. So this number, kappa 3, right now it's 0. We're getting exactly a bell curve. But if I bump up kappa 3, you will see that this distribution kind of skews to the left and to the right. So if it's positive, this is a positive skew. If I make the value of kappa 3 really positive, you see the whole distribution kind of like shifts back a little bit, right? So it's kind of smooshing itself a little bit to the negative side. So this is a positive skew. It's got like a pointy, sharp positive end. And if you calculate with this distribution, you say, I would like to know the difference between the probability it's bigger than 0 minus the probability it's less than 0. In our problem, that's exactly the difference between Alice winning and Bob winning. You can calculate that by this formula. It's 2 times kappa 3 divided by 3 factorial times the square root of 2 pi times sigma cubed. So kind of a nasty formula, but it tells you if you can calculate kappa 3 and you're able to use the Edgeworth series expansion, then you can calculate this probability. And because we know that in our Alice heads heads versus Bob heads tails problem, the kappa 3 is exactly the difference of the hanging overlaps, this is what lets us see that Bob is going to have an advantage over Alice because he has less overlapping than Alice. So this is exactly what you can do in this problem. Of course, you can skew both ways. If you had a different sequence, right? If Alice and Bob were set up differently, it might skew negatively, and then it's a little bit skewed the other way. Let's see, can I make the skew even more negative? So if it's a very negative skew, it's going this way, and you can see the whole distribution shifts a little bit to the right. And now this distribution is more likely to be positive than negative. And now we're ready to segue into my research on deep neural networks and using this type of Edgeworth series approximation in that situation. It turns out for my research, we don't need just a one correction term, we need two correction terms. So that's what this looks like. So now we're looking at not the Alice versus Bob game, but the output of a neural network that has n neurons in it. And you could imagine, just like the Alice versus Bob game, we're thinking of n is some large number, and we're trying to understand very precisely what the neural network does in terms of n. For Alice versus Bob, we wanted to get a 1 over square root of 2 pi n that was appearing. And for neural networks, we also want to approximate very precisely in terms of n. And in this situation, it's not enough to do the one-term Edgeworth series expansion. You need two terms. And that means you're not just doing h3, the third Hermite polynomial. You're doing h4, the fourth Hermite polynomial. And in general, the Edgeworth series expansion is an infinite sum of these. It turns out just the first two are very, very accurate. And it looks just like a Gaussian distribution with some tiny corrections that depend on the fourth moment. So here I have kappa 4, which is the fourth moment of the distribution. And if that is a little bit bigger or a little bit smaller, you will see the deviation from the ordinary Gaussian bell curve. So if this is a positive number, you get a distribution that is a little bit more pointy at 0. It sort of has more mass near 0 and a little bit less mass away from 0. So it's sort of like smooshed a little bit. And in contrast, if it's negative, then it's de-smooshed. So it's less likely to be near 0 and more likely to be spread out. It turns out neural networks tend to have distributions that look like this. They're more smooshed towards 0. And this is all in a precise way from my paper at this workshop. So let me show you some of that now. So here's a brief summary of the paper. It's called Improving the Gaussian Approximation in Neural Networks. And it's appearing in this workshop on the mathematics of modern machine learning at the NeurIPS conference. So here's like basically the result in one picture is take a neural network on initialization, so right at the beginning of training, before you've fed it any data, and let's try to understand the distribution of the outputs of every single neuron. Some people call this the prior distribution. It's the distribution before you start seeing data. But if you can understand this distribution extremely well, you can figure out how the data is going to affect things and how the network will learn. This is a little bit like saying, let's figure out where we're starting. And then if we figure out where we're starting and we know what we have, we can figure out where gradient descent will take us. So this is an important problem in neural networks to theoretically understand what they're doing by understanding very precisely where are they starting. And our main contribution here is doing this Edgeworth series expansion lets you have a more accurate approximation for the outputs at every layer. So this gray curve over here, these are Monte Carlo simulations of a neural network that has 20 neurons, and what is its output after one layer. And the old Gaussian way of approximating things is this orange curve, the old approximation, and you can see it's not quite right. It's kind of a little bit not high enough. Whereas our new fancy approximation is the Edgeworth series expansion, and it's saying that, okay, the distribution of the whole thing is more smooshed than you would think based on the old approximation. It's more likely to be at 0. And this gives you better error results. If you plot the difference between the Monte Carlo and the approximations, you see that our error is much less. Why do we care about this? This idea of having too much mass at 0 and kind of things being spread out differently than you would expect just by the Gaussian over many layers in a deep neural network will add up and cause really unexpected things to happen. So there's a problem called the vanishing and exploding gradient problem, which is when your network gets a very, very deep, sort of the gradients either get very large or very small. And in fact, they can have a log Gaussian distribution, and you can trace it back to this problem of there's a small amount of extra mass, things are non-Gaussian, and over many, many layers, this adds up and causes problems. So this is an important theoretical problem that I've worked on in the past, and this is kind of another way of explaining it. The main contribution of our paper, though, isn't this picture, it's this picture, the 2D version of this picture. And there's some much more complicated stuff going on here. You have to do a 2D version of the Edgeworth expansion. And it turns out in 2D, it's very complicated because you don't just have one Gaussian, you have a multivariate Gaussian that has a covariance structure that can be quite complicated. And when you do the Edgeworth expansion, you have to sort of take into account that covariance structure. You get some nasty looking formulas that took us a long time to work out, but you finally get some nice approximations. So over here is the error size between the Monte Carlo simulations of 2 inputs into the network plotted on this XY grid, so X1 and X2. And if you look as a joint distribution of the 2 inputs coming into the network and the 2 outputs coming out of the network, what is their joint distribution? You'll get a plot like this. So this is the error size between the Gaussian approximation and what the neural network is actually outputting. And you can see it's got this big black spot in the middle. That's because the Gaussian approximation is significantly underestimating the chance of these outputs being close to 0. In contrast to that, our Edgeworth expansion, the plot way over there, is showing you that you can fix it by adding these 1/n size corrections. And this kind of thing is really important for understanding not just how large the output is through the network, but the angle between 2 inputs. And so it's known that if you have a very deep neural network, as you feed 2 inputs into the network, the angle between the 2 inputs as they get fed through the layers of the network will tend to get more and more aligned. So you start with 2 images, a cat and a dog, and they're fed into your network. But after like 1,000 layers, they're the same output. The neural network has lost the ability to tell the difference between the cat and the dog. And of course, this is a real problem for neural network training. This is one of the reasons people use skip connections. Skip connections help with this problem a lot, but in a very deep network, it can still add up. So this is an important step, like a theoretical tool for understanding these kinds of network degeneracy problems that come up in very deep networks because small errors add up over many, many layers. So that's all I'll say about my my work here. There's a QR code if you want to check out the paper itself. The point is that we fix the error corrections, and now we have errors that are size 1/n squared. And when you have errors that are size 1/n squared, you can add them up over n layers of the network. So you can have the number of layers can be the same as the size of each layer, and you can still have an accurate approximation at the end of all that. So even though it's a lot more work to get these accurate approximations, they are much better for trying to figure out what's going on in the network. And the reason we care is because of this idea of accumulating error over many, many layers. Deep layers need more approximations. So the deeper your network, the more control you need. All right.